would like, so there were three talks today which have raised very interesting and fundamental, say, issues in hydrodynamics, in quantum field theory. So I would like to ask people to ask questions to all of the speakers. And from what I have seen, seen in the question time, there were say many comments about first of all in the chat about this the Wigner function, the negativity of the Wigner function, the positive of the Wigner function. So maybe I can ask Leonardo to say something about this. This was discussed in the chat quite vividly. Yeah. So so there were several questions in the chat about the physical meaning of the Wigner function. So whether it is a probability or not, or whether it can be negative or positive. And I think that this maybe Leonardo can say something. And concerning the talk by Andrea, there were several comments about this analytic distillation and the relation with other techniques in quantum field theory, and also interesting questions about the nature of the or the conditions of the equilibrium in the rotating equilibrium, accelerated equilibrium in George's talk. So maybe this is just a sort of so it is time to encourage people to ask questions that were unanswered and to add new ones. So please, is there anybody who want to start the discussion? So now I can stop sharing.
I guess I'll sort of try to make my question a little bit more concrete if I can.
Yes,
can
sure.
I?
Let me just.
Yeah.
I cannot. Okay. Yeah. Sorry,
I mean,
I have to. Just a moment.
Sure.
Yeah. Yes, please.
Yeah. This is sort of to the previous two speakers that, I mean, global equilibrium in this setting to me is a little bit like, especially global equilibrium with acceleration, rotation, and a free gas is a little bit of an engineered situation. I mean, it's nice to calculate and to have an idea what the density matrix is, but it's a little bit an abstraction because it's a carefully prepared system. I mean, the most that we can think of is a system of local equilibrium with the dynamics which produces a configuration similar to this. And it's possible to get it considering, I mean, if you consider the Zubarov statistical operator, there is a foliation. And there is a foliation in it. So there is a definition of tau. And the definition of equilibrium is when the quantum field obeys the KMS condition in the frame comoving with this tau, in a frame which is comoving with this tau. In these two situations that you guys examined, is this true for any frame? Can one define a frame like this? This is a question for the last two speakers, but sort of, this is to throw something to throw at the audience as well.
Okay, well, actually, I don't know. Maybe I can agree that the equilibrium with acceleration and rotation without any interaction is somewhat engineered, but also equilibrium without collisions. I mean, however, still there are some physical insights we can get from these operators, nonetheless.
Yeah, I mean, I agree with Giorgio saying that this is our engineer, so sorry, that these are special cases, so that the global equilibrium with acceleration and rotation, of course, they are, you cannot really make say a physical system where this is realized. However, they can tell much about the properties that the system may have a local thermodynamic equilibrium, at least when you have slowly varying fields. Therefore, I think that say they are very useful, and I have not really say understood why. So that I mean, I've never really say understood maybe my my limitation, this emphasis on the KMS condition. So why should a system which has not a equilibrium vector which is varying in space and time, why should it fulfill say a periodical condition which is typical of the usual thermodynamic equilibrium where for temperature is constant?
Yeah, I can answer this. I can answer this. This is because if you want, one thing it does, it proves stability. It proves that perturbations of the system stay small. I'm not sure if you take the density matrix that Andrea computed, for example, and perturb it a little bit, what will happen in general? Because, I mean, obviously it's not really a question that you can answer if you're considering a global equilibrium state, but it worries me. I mean, for example, in the last talk, you have temperature and acceleration, and acceleration in general is different. The Unruh temperature is different from the temperature that was put in. This is not a system which is in equilibrium in any sense. I mean, it might be in some kind of metastable state, but the Unruh bath and the temperature will talk to each other, and in general, they're not the same. So the KMS condition ensures that this stuff doesn't screw up your state. You see what I mean?
Can I say something about this? Yeah. Can I say something about this?
Yeah, please, Ho.
So,
please go ahead.
Yeah. So I think in the case of global rotating equilibrium, I think this stability should be somehow preserved by angular momentum conservation. I think this density matrix should describe equilibrium consistent with global amount of angular momentum which is conserved. In that sense, I think at least in quasi-particle picture, this density matrix should be robust even under collisions. I think just like the usual homogeneous equilibrium density matrix is robust under collisions. That's just my small comment. For the case of acceleration, I share the same question whether it is really describe equilibrium or not. I still have a question on that, but for global rotating equilibrium, I think is more robust, I think.
It describes equilibrium. It describes a very, say, a very unusual form of equilibrium, but formally, that as it is, known in the most studies of the Unruh effect, that the flow lines of the fluid, the uniformly accelerated flow lines, are field lines of a Killing vector. So even though, I mean, you have accelerated motion, then it is special relativity. It is equilibrium, and this is confirmed by the fact that if you calculate, said every scalar quantity along the field line is constant, for instance. So the moving temperature, stays the same along the field line. So if you have a comoving observer which is moving, he sees or she sees the same temperature at all times. And
I see. Yeah. Yeah. I
so
think I can.
it is formal equilibrium.
Yeah, I think I can accept that. May I have another question, maybe to the Andreas?
Sure, absolutely.
Yeah. So in the case of global rotating equilibrium, for example, the system is not homogeneous in space, right? There's a fluid rotating, and the fluid velocity depends on the position. I presume that somehow this position dependence is embedded in your Wigner functions as a function.
Also in the mean
momentum
values
T
also. Sorry.
Right. But suppose that we actually move the center of the global rotation from one place to the other by shifting the, just the origin. How could we see that information of the origin in your Wigner function somehow? Yeah.
Okay. So you're asking basically, I think moving the say the center of rotation, I think would imply to make a Lorentz transformation on the density operator. So you would have, I think, as usual, a term which accounts for the translation of the origin of the rotation, and then you can compute the mean value with this new density operator, which accounts for the different observer. So the density operator I've used in these in my examples, also in the while calculating mean values with rotation, was also always say an observer at the a particular observer, which sees the system with the thermodynamic parameters b mu equal to some constant term and the vorticity equal to the angular velocity in that system. Of course, if you change the observer, you have to change the density operator, and that will reflect on the mean values. I think this answers your question, I think.
Okay, so yeah.
Okay,
I've answered. Okay.
So I think these parameters in your density matrix are all constant, right? Beta, mu, and
yes. I mean, the global equilibrium. What I mean by global equilibrium is that when the parameters in the density.
Andrea, maybe you can share the screen if you want to.
Yes, maybe it's convenient. Okay, you are seeing my presentation now, I assume. So
maybe in the first few slides, I think you introduced the density matrix.
So these two guys here,
right.
B mu and omega mu nu, are my thermodynamic parameters, which describes this equilibrium. So if you say change the observer, you will observe a different equilibrium. For instance, this B mu is the Lagrange multiplier, which I mean, this density operator describes a system which has a fixed for momentum vector, mean for momentum vector, and a fixed mean boost angular momentum operator. And these are their Lagrange multipliers. So if I only consider the Hamiltonian, here I have B0H. So B0 is my temperature. And then I am considering a system with a fixed mean energy. Now, if you, and this is, this kind of situation was what I have always considered in my examples. If you say want to shift the rotation axis and what's not, you have to transform the operator so that you are describing a system which has some different characteristics. and so you will, from the original system with bit 0 h, you will end up in a system with a 4-vector p mu, and then you can compute mean values with this new operator. B mu and omega, however, are always constant.
So can I add a comment?
Please.
If I understand the question about changing the point of application of the angular momentum operator, we usually assume that J mu nu is with respect to the center of a Cartesian reference frame. And like in classical mechanics, if one changes the point of application, one has to take a different J mu nu. In particular, the difference between two operators J mu nu with respect to the center of the Cartesian reference frame or another point is just the distance between the two centers.
Oh, yes. Okay, I understand.
Anti-commutative, yes. A mu, P mu minus. So it would change in the point of application of J would just change the first row of 4 constants instead of having small b.
Okay, what happens is that J mu nu in this case of free fields and so on, you can write these like and that's exactly how you find this for temperature. So you write of course, P mu is the integral of T mu nu. J mu nu is the integral of x mu T alpha nu and so on, anti-symmetrizing, and making this substitution, you obtain this for temperature. So what you are saying is that if you change the x variable, right, you have a shift in this term, which can be absorbed in this B mu parameter.
Yeah, I
So,
think that answers my question.
I think you miss you. I mean, if you had the full covariant formula, then it would be easy to understand. Easier. I don't know if you have it in your slides.
No, unfortunately, I don't. However, I think what you are referring to is just like this. How can you say?
No, I mean,
so, so the translation of the origin of rotation corresponds to a translation in this x nu. X here is just the space-time coordinates. So you translate this coordinate by a vector, constant vector. I don't know, x. No, x is this y by a constant vector y. However, you can always absorb the contraction omega mu nu y nu into a new b nu. So,
I mean, this gives rise to the usual, say, formula of the shifted angular momentum operator, which is equal to the original one plus, and then you have the external product of, say, y and p. This is reabsorbed by b mu, which becomes a new constant. It's b mu plus omega mu nu y. And so eventually the form of the operator is the same.
Yes.
As the temperature and for velocity field would change, but the thermal vorticity would remain the same.
Yes. This B nu changes and the vorticity is the same. Okay. So I will stop.
There are questions by Masoud and Victor. Masoud, can you ask?
Yes. I wanted to ask about this, I mean, the electric part of omega mu nu. Are you assuming that this guy is independent of the temperature gradient?
What? No. Actually, omega mu nu is indeed the for temperature. You can obtain omega mu nu as the gradient of the for temperature. So I don't. Maybe I don't understand your question.
I mean that if we assume the equations of the ordinary hydrodynamics, you find that a mu times T is plus some T times gradient of, plus gradient of T is equal to 0, yeah? This is something like that.
I'm not really sure. I mean, this for temperature here is the Killing vector. Yeah, is a Killing vector of a general Killing vector of Minkowski space. And this is what I refer to as the temperature. Then this parameter is just some antisymmetric combination of the gradients of the temperature.
Yeah, I understand that.
You can of course, because this is a Killing vector, you have that the symmetric combination of gradients of these four vector vanishes, but maybe I don't see your point.
Yes, if that is the Killing vector, the temperature cannot have any, I mean, co-moving temporal gradients. Okay.
Yeah.
That is time independency, but
Yes.
it doesn't mean that it cannot have a spatial gradient. It can have something like that. Okay, so, and that the spatial gradient can be a source of acceleration. Yeah.
Yeah, it's correct.
Yeah.
Correct.
But again, if you go to, I mean, if here are these guys independent of each other, a mu and t?
A mu and t. Sorry, can you repeat?
If I understand the question, no, they are not independent. They are both fixed by d mu parameter and omega mu nu. In particular, the temperature gradient is collinear with the acceleration, and even the modulus, they are related.
So can we go to this
part of the Killing equation? It's a consequence of the Killing equation. Yes.
If we assume this equation of hydrodynamics from T mu nu and assume that we are in equilibrium, I mean your T mu nu, which has a mu inside it, I think.
Yes.
It wasn't page.
Let me here. These are the components.
Yeah.
Or maybe you meant this one.
The previous no. You had a form for T mu nu. Yeah, exactly.
Okay.
So the mu of this guy must be 0, yeah?
Yes.
And if we assume that and use ordinary Gibbs-Duhem equations, what we find for T, it's like a second order or second order. Yes.
First.
It looks like a second order T mu nu, yeah.
Second order, you mean in gradients of temperature? I don't understand.
Yes, in the gradient of temperature.
Yes, if you interpret this alpha mu as a part of the gradients of temperature, you have two first derivatives of for temperature, let's say.
So what happens if we assume the equations of motion here and find, for example, the entropy current, something like that?
I don't know. I don't know.
That's something quite new, yeah?
It has been known for some time that there are second order corrections in thermal vorticity, therefore in acceleration to T mu nu. This has been known for 10 years, I think. And of course, in this case, the equation of motion in the case of global equilibrium are fulfilled. Then if you promote these functions so if you promote this alpha mu to arbitrary functions, if you promote the velocity field to an arbitrary field, then of course I don't know what happens to the hydrodynamic equations. I think maybe they become unstable. I don't know.
Let me write the equation. Sorry.
Victor, can you please ask your question? Victor, can you hear me?
Yes, sure. Thank you. Okay, so we are at the slide where I wanted to ask the question.
Okay.
I would like to also remind people that there are 2 more talks, so that they're not. Okay, please go ahead.
Okay. Aside from this one, yeah, sure. So my question is related with this technique that you employed in order to extract a finite value from this sum.
Okay.
In this case, where the field is massless, the answer is easy. It's just sinh to the 4th in the denominator. But for a massive field, presumably the expressions will be more complicated.
Oh yes, you're right. You're right. And the reason is because of these integrals here. So in the massless case, the integral is easy. It's just okay. Here there are some more complications. However, if you consider in the scalar case, the Wigner function has no matrix-like structure. It's very similar to this one, just without these terms here. So once you integrate in the 4K, you obtain always expression which you can express as derivative of the tilde temperature, and then you can compute the integral in the 3P, and the integral is somewhat trivial, is 1 over beta squared, I think, or something like that, and you can compute beta squared and you obtain this. In the massive case, the integral is much more hard. I think the result is some Bessel function, K2 function, I think. And so in this case, the asymptotic expansion is much harder. Yes.
Much harder, and maybe also non-uniform, meaning that it may be illegal to switch some summations between themselves.
Okay.
This brings me to my question.
Okay.
From a technical point of view, so the concept is clear, but technically, what are the prospects for this more realistic massive case to apply this technique?
Okay, so we had. Sorry, Francesco. Okay, we had tried something in the massive case, but of course we didn't go too far because of these difficulties. A possibility to study the massive case maybe could be, I don't know, also to generalize this definition. I want to also to stress the fact that this is the very first definition we have given. We don't know if or even maybe there is a better definition in the context of resurgence, as I have said in the talk. So maybe, I don't know, expanding this definition would give some better insight. However, also in without doing anything like that, we have tried with the Bessel function to obtain some results. Actually, I don't remember if...
there are 2 more questions. I think that say we are slowly drifting to the end of the of today's session. So if you
okay,
want
I'm
to
sorry.
continue privately this
Turning the
discussion, I
mass.
think to give the
Okay.
opportunity to. I have to remind that there were 2 more talks today. So if you have, please ask questions to Leonardo and George as well. And
Thank you,
so
Andrea.
I would
Thanks.
like to
Oh,
ask
thank you for the questions.
I would like to ask
Oh,
Shubham.
yes. I have 2 questions. The first one is for the last 2 talks, especially the
Okay.
second talk. In
Okay, so
your
let's stop
derivation, you
sharing.
use the global equilibrium condition, namely the Killing condition for the beta field, beta mu. This is true only for the massive particle. For massive particle, I think the Killing condition, the global equilibrium condition should be modified to be the conformal Killing equation. Because for that case, the expansion or shrinking of the fluid does not drive the fluid after for equilibrium, which means the Killing condition should be changed to the what is called the conformal Killing equation. So I want to know how important is the global equilibrium condition is in your derivation to get all those results.
Okay, maybe so you are saying that in the massive case, the global equilibrium condition, so the Killing equation, the Killing condition must be modified. Is that your
For massless case?
For the massless case. But why are you saying that? Sorry.
Andrea, it can be relaxed. It can be relaxed to the conformal Killing equation.
Right. For massless case, right?
So that
yeah,
the
if
Killing
you
condition is stronger than the conformal Killing.
Yes. And if in this case, what would be, I mean, changed in your final result? Because you show some result for massless case, right?
Yes. Actually, I don't know. It's the first time I heard about this. To be honest, I'm a newbie in the area, so maybe Francesco has some more insights about this.
I mean, I don't know. Certainly, that if you so it would make, I think it will make certainly the calculation more complicated. Because it is more general. So I think that you have further terms appearing in the so we will have, I think, that in the exponent of the density operator, you will have generators of the conformal group as well, not just Lorentz and translations, right? Shubham, can you hear me?
Yes, I can hear you.
Yeah. So what I guess that you will have the conformal generators in the exponent. And then this will lead to say a generalization of this calculation.
Yeah, sounds interesting.
Right. This is what I guess. Because conformal group is larger, right, than the Poincare. Yeah.
Yes.
Okay.
Yes. Yeah. Should be interesting to see what will happen.
Yes.
Oh yeah, it is. Yeah.
Yeah. Thank you. Yeah. My second equation is for Leonardo. In your talk, you showed that the Polarization vector can be used to define the spin polarization. And this vector, by construction, should be pseudo-gauge invariant. But the final result is given by, if I remember, this vector is given by the Levi-Civita tensor times P nu times S rho sigma. How can I, from this expression, that this is a pseudo-gauge invariant? Because if I do a pseudo-gauge transformation, this S rho sigma would be transformed, but
maybe
how would this P?
The...
Yes, please.
Yes. Can you see this?
Not yet. I think maybe a few seconds.
Second, try to share the. Can you see now?
Not yet. Yeah, maybe
I
I
can
need
see
to
it.
wait a few seconds. Yes,
I can
yeah,
see
now I see.
Leonardo. Maybe
Yes, I can see it.
take some time. Yes.
Yeah, I can go to the point when I talk about the Pauli-Romansky vector.
Right.
Here. I think the easiest way to see that the polarization is not dependent on the pseudo gauge is that it depends on the global charges, not on the currents. So the total for momentum operator and the total angular momentum.
Okay, let's say the second line, the formula with a box, the pi mu.
This one.
Right. The last equality, you have the S nu rho and the P sigma.
Oh yes, this is the one for classical particles. Yes.
Okay. How can we make the pseudo gauge transformation to this expression?
We cannot, because this J mu nu in the top box is the total angular relativistic total angular momentum of a classical object, extended classical object. There are no stress energy tensor at this level or anything. This could very well be the relativistic extension of the Earth-Moon system, in which the Moon rotates around the Earth. That's the x dot external product with P. P is the total momentum of the Moon, and S mu nu is just the rotation of the Moon over its axis. The pseudo gauge transformation would involve the quantities that integrated give us the global conserved charges, J mu nu and P sigma, J nu rho and P sigma, but because of the definition of the pseudo gauge transformation, they cannot change the conserved charges. Differently from other proposals and approaches in this presentation, I never made something like a momentum density of angular momentum or stuff like this.
Okay.
There was something like a phase space density of angular momentum to obtain the polarization vector.
Okay. Then what if we put the single particle expectation value of the pi mu operator on a single particle state with a momentum p? Then this P sigma would be just the P, right?
Yes, that's something that is done here. I skipped the calculation, of course, but it's a little problematic to use eigenstate of momentums, because you see that you would have something like a delta square. It's better to use a full wave function, this psi1, which is a one particle wave function. Then instead of a delta square, it is just psi complex conjugates times psi, and it's regular and there is no problem. This is just straightforward, if boring, computation from the basics of quantum field theory.
So finally, you will result in
pi mu has the global conserved charges, never the densities.
Okay. Then finally, if I want to, for example, this formula that all those numerical calculations used, which express the polarization as a function of momentum p of the particle. Would this still be pseudo gauge invariant?
You mean this formula in the box in the middle?
Not this one. I mean maybe the one that you derived with Becattini and Grassi. You know
the one by Becattini, Del Zanna, Chandra, Grassi.
Yeah.
Okay, maybe if I understand the question, because this slide is just for single particle states.
All right.
But this last one is for a generic one, for the polarization. Okay, using the ansatz on the Wigner function that was used in the paper by Grassi, Becattini, Grassi, Del Zanna, and plugging it here, one would obtain exactly the same results that they had. They didn't use this approach at the time. They made some ansatz on the phase space density of angular momentum, but actually it can be proven that I think that Francesco, you put it in your paper here that is cited.
Yeah, right. The maybe I can add that this so in this formula, this expression is independent of the pseudo gauge. So it means that this is it does not depend on whether you use spin tensor or not. When you come to the value of the so when you come to evaluate the Wigner function at some local equilibrium, then it's when it is when problems of pseudo gauge equivalence arise. So in other words, this expression formally is independent of pseudo gauge. Okay, but I think this will be discussed later in the week. I think there will be a talk by Enrico Speranza about this. And when you evaluate then W, then you may have corrections due to the fact that the local equilibrium can be defined differently if you have different pseudo gauges. I don't know if this was the question.
Oh, yes, yeah. That's
okay, so but let me then take the opportunity, since this is the time is up for me. Then this is a very interesting discussion. So I have to go, but if you want to continue this discussion, I can appoint a host replacing me so that you can continue the discussion in this session. And eventually you have to end the session. So is there anybody among, for instance, Leonardo or Xu Guang or any other?
It works for me.
Leonardo, can you be appointed host?
Yes.